Hello everyone, today we are excited to share our project titled MPC Control to Avoid Obstacles. I'm Xie Zong and this project was completed with my teammate Zhou Guancheng. Our focus is on using MPC to help an autonomous vehicle safely navigate around obstacles on the road. We also compare the difference by changing the obstacle parameters and ensure that there are no issues with this project. Our implementation is done in MATLAB. First, we initialize system parameters and created a direct time vehicle model. Then we define a road environment, especially the lanes and obstacle positions. Next, we set up the MPC controller, define reference signals, and finally simulate the vehicle's movements with visual output. To model the vehicle, we start with a nonlinear car model and linearize it using the Jacobian method. This gives us the continuous time system, which we convert into a discrete time model using linear order Holt. The result is a system that's well suited for MPC and can predict how the car responds to acceleration and steering commands. We define a 3-lane road and with each lane 4 meters wide. We also calculate the safety zone around the obstacle, which is important for ensuring the vehicle maintains a safe buffer when playing maneuvers. The initial driving scene is visualized using MATLAB plots. The obstacle appears as a red rectangle with a dashed safety zone around it. Lane boundaries are marked with dashed blue lines. We then set up the MPC controller using the discrete model, turning off verbose outputs for a cleaner simulation.
Let's start with the MPC setup. Here we define a prediction horizon of 60 steps and a control horizon of 2. We also set rate constraints for both throttle and steering to ensure smooth operation. Additionally, we apply appropriate scale factors and output weights to emphasize vehicle speed and let road position. Finally, we set the nominal conditions of the system using the model's current states and inputs. Now we define mixed input-output constraints which are key to handling obstacle avoidance. We construct inequality constraints to keep the vehicle within road boundaries and allow for dynamic lane adjustment. These constraints are defined by matrices E, F, and G and are passed to the MPC controller using the setConstraint function. In these steps, we define a constant reference signal. This represents the desired trajectory of the vehicle, in this case driving straight at a constant speed. We also initialize the state and input variables, and set the simulation time steps. Here's the core of the simulation, the main control loop. At each time step, first we update the plane model based on the latest vehicle state. Second, we detect any nearby obstacle. Third, we compute a new set of constraints based on the obstacle position. Then we generate a new plane model and nominal conditions for MPC. Finally, the controller computes the optimal control move and updates the vehicle state. This allows the vehicle to respond dynamically to any obstacle ahead. This function checks whether an obstacle is within detection range, and in the same lane, it considers both the Euclidean distance and the lateral position of the vehicle. Only when all these conditions are satisfied do we consider the obstacle detected. Once an obstacle is detected, we dynamically compute new constraints. We calculate the slope between the ego vehicle and a designated safe zone beside the obstacle. Depending on whether we are behind, beside, or past the obstacle, different constraints are applied. These constraints help guide the vehicle around the obstacle, either to the side or back into the lane afterwards. If no obstacle is detected, the vehicle simply follows the default lane boundary. This is the continuous time dynamic model of the car. We derive state space metrics based on the car's current velocity, handling angle, and steering input. These dynamics are used in the background to build the discrete model used in the MPC loop. To visualize the result, we plot the MPC trajectory and the dynamic constraints. The green dashed lines represent the constraint boundaries that adapt in real time as obstacles are detected. The black curve shows the actual vehicle path. As you can see, the vehicle successfully avoids obstacle and returns to the center lane. So here we've got two different results. The only thing that changed between them is the size of the obstacle. When we run both cases through our adaptive MPC controller, you can see the vehicle takes a different path. A bigger obstacle means the car needs to steer more to get around it, which causes the noticeable change in both the steering angle and the throttle commands. Basically, the bigger the obstacle, the harder the car has to work to stay safe. It's not just about the path, it also affects how the car accelerates and turns. It is our reference source. Thank you for your attention.